Good afternoon, everyone. Thank you for joining this afternoon session at the 2023 ESIP conference. Those of us in the room, we're getting started promptly. If you could please take a seat so those in the room can hear. Welcome everyone online, those of you that have joined virtually. My name is Jenny Disson. I work for a NOAA Cooperative Research Institute that is part of NOAA, NCEI, and also the engagement lead for the NOAA Open Data Dissemination Program. Thank you for joining our session. We're going to be talking a lot about climate services with NOAA data in the cloud. Thanks for being patient as we got set up for this session. We have a blended virtual session with videos, virtual presenters, and with me, with the rest of the team in the room. It's a pretty exciting discussion because we're going to be talking about what happens when you put NOAA data in the cloud. So with that, I would like to welcome our very first speaker, Adrienne Simonson, who is the director of the NOAA Open Data Dissemination Program. While I pull up her slides, I think she will take a second or two to introduce herself.
Well, thank you so much, Jenny. Good afternoon, everyone. My name is Adrienne Simonson. I'm the director of NOAA Open Data Dissemination, and I'll be providing a brief overview today of NOD, focusing on our user engagement efforts with partners and other stakeholders, thus highlighting the value of providing open data access via the cloud. We're good, Jen. I can see it. You probably just want to go into. Oh, okay. All right, great. Well, so NOD is an enterprise service option that disseminates NOAA open data. The data must be quality data of value to the public, and there cannot be any use restrictions. User registration is not required. Appropriate metadata is provided. Most significantly, there are no egress costs for the users or for the agency. And because NOD serves the data outside the NOAA FISMA or security boundary, the data is easier for users to access and allows for interoperability and innovation. Next slide, please, Jenny. Let's take a look at the NOD architecture. On the left side, there are pictures representing the data and the observing platforms by which NOAA collects that data, all within the FISMA or security boundary. Because the NOD cloud buckets are outside the NOAA security boundary, a trusted third party must own the buckets. Could you go back, please? Yeah, great, thank you. Follow the arrow to the right to find Success, NOD's trusted third-party data broker. Success is allowed inside NOAA's security boundary to retrieve data sets, which it then transmits to the cloud service providers, or CSPs. The CSPs then provide free access to an exponential number of users, enabling their innovative data analysis and decision-making. Success, a NOAA Cooperative Institute, brings deep subject matter expertise and understanding of NOAA's missions and data sets, in addition to its cloud and engagement expertise. Success sets up the NOD bucket infrastructure, pulls the data into the buckets, monitors data flows, resolves operational problems, supports the development of statistics and metrics to monitor dataset usage, and helps to certify select CSP holdings as authoritative NOAA data. NOD is both agile and cost efficient, disseminating and monitoring data 24/7, utilizing software to notify the data broker if there are any issues. The notification and response is customized based on the severity of the event. So if the infrastructure crashes, they'll be alerted and start working on a resolution immediately. While NOD uptime also depends on upstream NOAA data provider systems, the data broker has worked extremely hard to build in safeguards and redundancy, for instance, pulling from backup sources if those upstream feeds go down. As a result, NOD often exceeds the uptime of individual sources. Next slide, please, Jenny. NOD accelerates open science by providing open data and open access to environmental data, research products, and results, and provisions new data, thus ensuring an open scientific process and reusable analytics pipelines. This approach incorporates the fair data principles. In addition, NOD relies on and incorporates open source and source available software. Interoperability of diverse data sets is key to supporting users and driving innovation, and cloud-optimized data formats make the data more accessible in a performant manner, saving researchers and private enterprise time and money on compute costs. To support the reformatting of NOAA native formats by users or other partners into cloud-optimized formats, the data broker establishes research and development pathways, and the CSPs provide platform credits. The converted data sets are then made available on NOD in addition to the original data set. Note as well that stakeholder communities are forming around the conversion tools, further enabling innovation and advancing interoperability. Next slide, please. NOD leverages the CSP's expertise, platforms, and tools via unique public-private partnerships that democratize NOAA data dissemination. This slide includes a shot of each of the CSP's public dataset programs. These are the programs that bring the data to the end users, so NOD works closely with each of them to ensure accurate information is provided. This information is a starting point for the user and often also includes usage or code examples and a list of publications relating to the data set. It also provides contact information for our team and in some cases directly to the data points of contact. Note that data being disseminated through NOD is extremely reliable. The CSP storage bucket availability guarantee is well above 99%. This is provided through the base customer service level agreement that all CSPs have with their customers, including NOD. Second, the cloud buckets can support extreme amounts of data requests, such as terabits per second, and users don't impact each other's experience in accessing the data. Next slide, please. There are hundreds of NOAA datasets available via NOD from across NOAA. I'll let you read the full list of the types, but want to highlight that it includes near real-time datasets that can support user operations. NOD also often builds a full period of record for select data holdings based on CSP and data provider requests. A full list is available on the NOD website, which includes direct links to the landing pages. And I'll take a moment to note that we hit 35 petabytes this week. Next slide, please. In the past, NOD and NESDIS served a subset of archived JPSS data on AWS. Now NOD and NESDIS are making real-time JPSS data available on all three CSPs. These polar observations provide information that are key to the development of weather and climate predictions. This is a critical data set in support of administration priorities and also reveals the smoke plumes from Canadian wildfires over the US. Note the large volumes of data available. Next slide, please, Jenny. This slide shows the recently developed links to the relevant CSP public dataset landing pages or how to directly access the near real-time JPSS data. I believe you all will have access to these slides and it may be a week or two before our website is updated. So here's the information. Next slide, please, Jenny. Data only have economic value when they're used in decision-making. And now that the data is in the cloud, cloud users, like an archetypical NOD data user, look to NOAA for data, information, and tools in order to use the data in decision-making. But their needs vary across the board, across sectors, and across levels of experience. Some are looking for answers or guidance, some need training, and some want a helping hand. NOD provides continuous service delivery and also serves as a customer experience function, reaching users via the cloud. NOD provides timely and informative responses to user questions, as well as technical and scientific support, and loops in internal data owners and stakeholders, including CSPs, when appropriate. Users can opt for service delivery notifications of the data sets as well. The CSPs are also interested in understanding their user community's needs and collaborate with NOD to provide technical as well as communication and engagement tools to reach users, inform them that data is available, and answer their questions. NOD is continuously looking for ways to connect with our users in order to understand their experience and improve it. Targeted user engagement activities include webinars, cloud training opportunities, participation at flagship conferences, and a new concept called office hours. Next slide, please, Jenny. Office hours are a new low-pressure user engagement method developed by Jenny Disson, NOD's engagement lead. The simplicity of office hours is a big hit because users are afforded the opportunity to ask questions and listen to other users asking questions of the dataset subject matter expert, the CSP, or NOD from the comfort of their own desk. First, a little background. In January 2023, NOD held its 8th AMS town hall and heard from several high-resolution rapid refresh, or HRR, model data users, like Kate Duffy that will be following me. They were interested in understanding Weather Services' plans for its transition to the Rapid Refresh Forecast System, or RRFS. Users wanted to understand the impact of that transition to their current use and business models. NOD worked with AWS and the National Weather Service's Office of Organizational Excellence to host office hours focused on HRR, pulling together both the on-prem users and cloud users from public, private industry, and academia. Subject matter expert Jeff Manikin provided information on the transition plans and invited users to stay informed and connected via the subscription information. About 40 participants met for an hour and provided comments on their use of HER, its value to their operations and their experiences, and got their questions answered. Next slide, please, Jenny. The second office hours was focused on precision marine navigation, specifically the S100 and S111 data sets, or forecast guidance of surface water currents, in collaboration with NOAA's National Ocean Service and AWS. The speakers included the Office of Coast Surveys, Julia Powell, who is the Navigation Services Division Chief, Darren Wright, the Precision Navigation Program Manager, and Dr. Greg Soroka of the Coast Survey Development Lab, and AWS's Chris Stoner. Participants included in the ocean and blue tech industry, government and academia who are working at the crossroads of data science, cloud computing, and data access for its use in decision making. And based on the questions, clearly found this 1 hour event helpful. Next slide, please, Jenny. NOAA is working with all of the CSPs to provide similar opportunities on targeted data sets offered on their platforms. The next or upcoming office hours is scheduled for August 16th from noon to 1 p.m. Eastern Daylight Time in collaboration with the National Weather Service's Office of Organizational Excellence and Google. Users will have a chance to connect with subject matter experts on the Global Ensemble Forecast System, or GEFS. Speakers include Alicia Bentley and Yuijian Zhu from NOAA's National Centers for Environmental Prediction, or NCEP, and Google's Antonio Lobato. Users can register and submit questions in advance by emailing NOAA at nod@noaa.gov. We hope you will join us. Next slide, please. Before closing, I want to first recognize ESEP for its unique contributions to federal agencies and for its understanding and agility in response to our ongoing challenges. Theirs is not an easy task. I would also like to highlight the natural partnership between ESEP and NOD to connect to and support users while advancing open data. For example, NOD and ESEP co-developed the NOAA Cloud Pathfinders Program, or NCPP, to provide a sandbox environment for NOAA scientists to build and experiment with their projects in the cloud. This is a proactive, project-based approach using cloud-native tools within cloud-optimized systems. It relies on a cohort structure and collaborates closely with the relevant cloud platform to provide detailed support and expertise for project needs, along with cloud credits. The demonstration cohort in fiscal 22 included 5 projects from across the agency. This cohort continued the efforts into a second term and was very successful, with one project actually moving into production. The Oceanography at Sea Information System, or OASIS, is an operational success within the National Marine Fisheries Service. Note the survey and Bigelow pictures on the right, as well as OASIS in use. NOD is working with NOAA's Cloud Program Management Office to find funding for the continuation of this program and anticipates the programmatic cohort will begin in late fiscal 24 or early fiscal 25. NOD is in conversation with the other CSPs on this approach, but I'd especially like to thank AWS and Chris Stoner, Public Dataset Program Lead in attendance today, for the support of the initial demonstration of this much needed program. And NOD is also looking to ESEP to support its user conferences in the future, including webinars focused on notebooks and the facilitation of conversations on cloud optimized formats in collaboration with other partners or stakeholders. One more slide. But we'd love your feedback. Jenny, if you, we'd love your feedback on open data access. This is for both ESEP and NOD so that we can better serve data users. Please use this QR code to let us know what you think. And that's it for me. Thank you. And back to you, Jenny.
Thank you, Adrienne. That was terrific and very helpful. For those in the room, we are circulating a flyer with the QR code. Please have a look. Simple questions. Welcome the opportunity to connect and continue the conversation. For those virtually, my colleague Kate will be putting a link to this form so you can also access, and there's plenty of other links. Putting NOAA data in the cloud is what helps us get access to the data for decision makers and planners to help advance the change that we want to see in our society. So with that, I want to introduce us to our next speaker, Kate Duffy, who is a co-founder of Zeus AI. As I transition and let her share her slides, I just want to take a minute and mention and thank Kate, who's been part of the NOD team conversations representing the user perspective on several of the NOAA datasets that she and her team are accessing via the cloud. Kate, the screen is all yours. Excellent. Okay. We can see it large, and I am going on mute. It's all you.
Great, thanks, Jenny. Yeah, so I'm glad to be here to provide a user perspective on how at Zeus we're using NOAA data in the cloud and cloud computing for our work on AI-based weather forecasting. So TJ Vandal and I founded Zeus last year in 2022. Prior to Zeus, we were both research scientists at the NASA Ames Research Center. And that was where I started working with geostationary data for applications to earth science, including weather monitoring, retrieving weather variables from geostationary data and similar. And that was where I started learning to handle big earth science data sets and set up machine learning workflows on the on-premises HPC at NASA. So when we spun out Zeus last year after we were awarded the NASA SBIR, we started building those ML pipelines on the cloud using a variety of different services on AWS. And throughout that process, having access to the NOAA data on the cloud has been really critical to our work. So a quick overview, I'll discuss the forecasting product that we're building, and then I'll describe the cloud products that we use for training models, for storing and accessing data, performing validation, and managing data access for users. And I'll also try to highlight throughout which NOD data we use and how it makes our research and development costs lower and lets us do our work. So at Zeus, we're working on developing machine learning-based approaches for data assimilation and weather forecasting. So we're using a variety of different NOD data sets, from satellite observations to numerical model simulations stored on the cloud. And we're using these different modalities of data to try to develop machine learning techniques that can really make use of this huge amount of basically unlabeled data from geostationary satellites. And perform both data-driven data assimilation and forecasting. So we're working on predicting our own initial condition using the every 5 to 15 minute geostationary scans of the Earth, and trying to learn representations between geostationary data and the kinds of geophysical representations used in weather models. And then also performing the forward processing of forecasting. And there's obviously been a lot of work in this space with machine learning already being the state of the art for short-term forecasting of many weather variables. So our product is called Low Latency Environmental Prediction from Neural Systems. That's our platform Lens that we're building as an end-to-end AI system for assimilation and forecasting that can run in near real time using machine learning models and cloud computing. And this model should be applicable wherever geostationary satellite is available, which is nearly global. And it can execute a lot faster than the numerical weather models that it emulates, which makes it possible to run a very high resolution model of 2 kilometers horizontal resolution and 15 minutes temporal resolution that refreshes every 15 minutes at this almost global scale, which is a lot bigger than that possible for numerical models like her that run at a high resolution regionally. So our forecast has a number of variables: surface temperature, air temperature, multi-level winds, solar radiation, radar, relative humidity, and more. The list is constantly growing. And currently we have a short-term forecast in the 3 to 6 hour range, but we're making steady progress to extend that horizon out over time. So that's our product we're working on. And on the technical side, we're working primarily on Amazon. and one smaller compute provider, Lambda Labs, for all of our data storage and access and computing. So on the data side, we access several different NOD data sets on Amazon S3. We use the GOES data, which is in NetCDF format, and her data, which is in GRIBs. And it's really helpful for us to be able to access this, both historical data for training and the real-time feeds for inference and production. And it's really helpful that there's no egress fee, and the transfer to EC2 compute instances is free, which is really helpful since we're looking at usually like really large terabyte scale training data sets, which would have not an insignificant expense if we need to transfer them, such as to Lambda Labs. And then we have our own private buckets on S3 where we store our geospatial data, training data, and inferences. And for our own data, we really favor the ZAR format, which can store multidimensional arrays similar to NetCDFs, but in a compressed and chunked form that allows us to selectively load just portions of the data that we're interested in, like by variable or by space and time, or however the data is arranged, which is quite fast and efficient. Then for our machine learning development, we use GPUs both on EC2 as well as on Lambda Labs, which has a bit newer hardware and lower cost. And we use a Conda environment on our compute instances, but we have to also use Docker on Lambda Labs since they don't have persistent storage. So that allows us to quickly set up the computing environment. And the production is also running on AWS, where we can quickly and with no cost access the NOD data that our models are dependent on for forecasting, and then go back and store the forecast data on our own private bucket on S3. So some more data stuff. We also use the Amazon Relational Database Service to store our point-based weather observations that we use both for validating our forecasts and for benchmarking the improvement of different model versions that are trained. We have it set up as a SQL database where the observations can all be indexed by time and location, so they can be queried efficiently. And using this database has helped us really build up our analysis tools and scale up the validation. And then finally, we're using the API gateway as a front end to the REST API that we have set up for accessing our weather data on S3. So using Gateway, we can provide API keys for users and then make sure that only authorized people are interacting with the API. And Gateway also provides some logging and monitoring capabilities. So we can track how much usage everyone is using or control the number of requests and so forth. So this is an overview of our training pipeline. Starts with data stored in NetCDF or ZAR files on S3. We are using XBatcher to generate batches from the Xarray objects read from ZARs and NetCDFs. And the basic usage of XBatcher is to define the chunk size along each dimension of the data, whether that be latitude, longitude, time, pressure level. And then XBatcher can automatically iterate through the data to serve training data sets to PyTorch. And I'll also highlight that we use some tools from Pangea, which is an open source software project that I believe we might hear about later in this session, that integrates things like Xarray and Dask, which is helpful for doing distributed analytics on large data sets because they don't actually need to be loaded into memory with Dask. And our machine learning models, we define in PyTorch or PyTorch Lightning we've been using more recently. And after training, we store the models weights back on S3 where we can access them for inference or production on different instances. So that's a bit about the product we're generating and how we're generating it. But what it's all about is trying to bring a benefit to these end users who are making decisions based on weather. So solar and wind energy production are very variable throughout time compared to the production from something like a fossil fuel plant. So accurate weather forecasts are really critical to help system operators, one, anticipate how much energy will be generated, and two, try to predict energy demand based on demand for heating and cooling that's tied to weather. And all of this also leads to dynamic pricing in energy markets. So weather forecasts also have a lot of value in the energy trading space. So this API that I mentioned is how we get the data to customers. Our API is built based on Fast API and deployed through the Amazon API Gateway. And users with keys can use actions like get with their API key to return data from some given location, time period, and variable as a JSON. And this allows fast access from our data into the hands of users and is interoperable with whatever systems they have on their end. So that is the end of the talk. Thanks for listening. I'd like to acknowledge our funders and provide my email address if anyone wants to follow up. Thanks so much.
Thank you, Kate. That was pretty super. I appreciated the list of the NOAA data sets that you're accessing via the cloud, and also appreciated the visualization that you embedded. So thank you for that. We are going to pull up a video for the next two presenters. They're from our cloud partners. Tom Augsburger is from Microsoft. He is a geospatial engineer. Before I pull up his video, just a gentle reminder for everyone in the room, if you can pull up the ESIP document associated with the session and identify your name so we can see who all was here for any follow-up or questions. Those of you online, also my colleague Kate will be putting in the link to the document where you can also identify your name with the session. That would be very helpful to us, especially as we reach out for other topics. Okay, so we are now transitioning over to Tom Augsburger's presentation, and I'm gonna have to do this carefully. Let's see, minimize the screen and share. Share. Where's Tom's? That's Chris. Nope, I think we had already pulled it up on the desktop.
Cloud native geospatial, Pangeo, planetary computer things. If you're not familiar with the planetary computer, there's three main parts to it: data, APIs, and compute. And this applies generally to any kind of cloud native geospatial. Hello, everyone. Thanks for having me. My name's Tom Augsburger, and today I'm talking about cloud native geospatial, Pangeo, planetary computer things. If you're not familiar with the planetary computer, there's three main parts to it: data, APIs, and compute. And this applies generally to any kind of cloud native geospatial thing. For the planetary computer, starts with the data. We host a whole bunch of geospatial data in Azure that's there ready for you to use. There's satellite imagery data sets, climate and weather data sets, biodiversity, lots and lots of different types of geospatial data there in blob storage for you. I want to talk a bit about how you might go about accessing that data. In the Pangeo community, we like to talk about this idea of these two different models, ways of working with data. So first of all, there's the download model. And under that model, the idea is there's files out there somewhere. Could be on the cloud, could be on some FTP server. But there's an initial stage of your workflow where you go out and you download all the files. And then you have your actual kind of analysis stage where you're loading the files from your local workspace, wherever that's at, on a laptop, on an HPC system somewhere. You're going out and you're loading those files and doing your analysis. But the key thing here is that there's these two very distinct phases. This is okay for smaller and static data sets. It does mean that like every group hoping to do the analysis needs to go out and do that download stage themselves. You end up with a bunch of copies of the data floating around. And the real challenge is when you try and work with large data sets or data sets that are updating rapidly, it can be hard to keep those in sync with the kind of upstream data source. Contrast that with the cloud native model where the data kind of just stays where it's at in blob storage in this case. And you move your compute to the data. So you place your compute in the same region as the data. That ensures that you have a nice high bandwidth connection between where the data is at in blob storage and your compute service, which might be using Jupyter or Dask or whatever compute you want to use. This is great because it scales well because thanks to the magic of Azure, its ability to scale, and we don't need every single group hoping to do the analysis on the data to kind of maintain their own data pipeline. It's kind of just there. Everyone has access to the latest copy of the data. But just having those files there in blob storage, even if they're in nice cloud optimized formats, isn't quite enough. If you imagine a task like finding all of the Sentinel-2 L2A scenes over Wyoming in 2022, when all you're presented with is like a list of files in blob storage, this is unreadable, but these are some prefixes to Sentinel-2 scenes in blob storage. It's like, where do you even start to figure out, like, does this file overlap Wyoming? What day was it captured? Things like that. It can be a real challenge, and each satellite provider has its own kind of naming scheme for imagery, and like you'd have to completely reinvent your workflow if you wanted to swap in a different data set. So that's where our APIs come in. So in this case, we're showing the Planetary Computer Stack API. Stack is the Spatiotemporal Asset Catalog. And with this stack metadata, which I'll talk about in a second, in the API, it becomes a pretty straightforward translation of your task to the code. So in this case, I want all the Sentinel-2 L2A imagery that intersects with my area of interest. It could be a GeoJSON polygon describing Wyoming from the date time 2022. And you can even do things like query on additional properties that's available in the metadata. So ESA classifies each scene according to how cloudy it is, and so you can filter it down to scenes that are less than 10% cloudy, say. Once you have those matching stack items, it's, again, a line of code to go from those to your kind of data container of interest. In this case, let's say you want an X-array data array, you can use stack to translate those stack items, which are just metadata descriptions of scenes, into an X-array data array. In R, there's the sits library to go from stack items to data frames, same sort of idea. This is a really powerful combination, the idea of the stack metadata and APIs. In this case, we're showing an example using Sentinel-1 RTC data from the Planetary Computer Explorer, which is just a JavaScript application. And it's in the background kind of making a bunch of stack searches as you pan and zoom around the map, filter on different date times, things like that, and using our data API to render imagery to a map. Or in this case, stitching together a bunch of imagery into an animation. In this example, we have the Microsoft Building Footprints dataset. That's a vector dataset available as GeoParquet and vector tiles. And we can overlay that vector data on top of Sentinel-2 satellite imagery. And again, this is, it's not doing anything special. It is just, JavaScript on the front end, using those stack APIs to do the searches as you pan and zoom around, using the data API to kind of render the imagery onto the map. I want to turn now to a demo in a notebook. So I've got a Jupyter Hub deployment in Azure in the same region as the data. And it's enabled with Dask Gateway, so I've gone ahead and asked for a cluster here, and I've got my cluster of workers to do a medium-sized computation later on. We're going to be working with the NOAA's OI SST sea surface temperature data set here that you can check out on our data set details page. And we'll go ahead and do a search for these OI SST items from June 2023. We go out and do that when we see the 30 items, so the one per day that match our query, which we can load into an X-ray dataset, in this case using ODC stack. And we can do something like grab the most recent item and plot it on a map. Okay. Now let's say we want to do something a little larger. Maybe we want to get the data for every June going back to the start of the data, which is 1982. We'll go ahead and do a batch of searches, one per year. We'll flatten that list of items into a list of items and load those into an X-ray data set, where now we have a time series going back to 1982. And you can see the time series here, 1982 to 2023, just June. And we've got our data array of items here. Okay. Now this is where our DAS cluster kind of comes in. If we look at just the first item, that's pretty quick. Last item, that's pretty quick as well. We're going to take the average anomaly over the entire globe, and we'll get back a single number for each timestamp. If we want to do that for the entire computation, take a bit of time, but with the cluster, it churns through it pretty quick, loading the data, doing that mean reduction over the globe, latitude and longitude, and getting back just the same number, which we have a time series that we can plot. Okay, so kind of wrapping up here, planetary computer and cloud native geospatial more generally, they really do start with data in blob storage. It gives you great high performance scalable access to the data. But we feel like it's really important to also have APIs to let you query and visualize the data. Okay, so our APIs are based on Stack, Spatial Temporal Asset Catalog, and that's what lets you do things like find me the data from this date time or intersecting with this area of interest. Our front-end Explorer tool is using those APIs, the Stack and the data APIs, to find the data, matching your queries, intersecting with your browser window, and visualizing those on the map. It's a really great way to kind of gain familiarity with the data set, understand what's going on. And then, of course, you've got all the computational power of Azure and libraries like Dask or Spark to do your actual analysis at scale for these really large data sets. Thank you for having me. If you have any questions, my email's here. And if you have any interest in the planetary computer, check it out at planetarycomputer.microsoft.com. Thanks.
Okay, so that was a really good example of how a different NOAA dataset called CDR, Climate Data Record, referencing OISST dataset, which is our ocean temperature dataset. And I really appreciated how Tom's video really captured what's been going on in June. So that was a really good example of how planetary computer and the Microsoft tools going all the way from storage to analysis to visualizations can be used as a way to draw value to the data that's in the cloud. So with that, I'd like to shift over to our next speaker, who's also a video, Chris Stoner, whose name you've heard as part of Adrian's introduction. Chris Stoner, who's pretty instrumental with ESIP here and has been working with NOAA and the NOD team, regrets she had to leave out early today, but has very quickly recorded her presentation and will be talking about some AWS data in the cloud and how to access that. So.
Chris Stoner. I'm at the AWS Open Data Program. And I'm going to show you today the NOAA datasets in the Registry of Open Data on AWS and a little bit about the SageMaker Studio Lab capabilities using NOAA NextRad data. So we'll start with the Registry of Open Data. It's at registry.opendata.aws, or you can just use this handy QR code. The registry has, at the moment of this writing, middle of July, 455 data sets. That's over 100 petabytes of data, free and open to the public. And the data in the Open Data program is split into roughly 4 pillars. There's the environmental data, geospatial data, health and genomics data, and statistics and regulatory. And we're going to talk today mostly about the environmental and climate space, and namely around the data in the NOAA Open Data Dissemination Program, or NOD. So the NOD program has its own, what we call a collab within the Registry of Open Data, and you can get to just the NOAA data sets within the NOD program by clicking this link here on the About page. And you'll see the title bar change to Collab NOAA. And really all we've done is filter the catalog of data sets that are in the registry to the 48, as of this writing, though it's growing, data sets that are specific to NOAA. And this includes GOES, NextRad, of course, Operational Forecast System, JPSS, and a host of others. And we're going to start really by looking at a couple of the capabilities that you can do from within your web browser and a little bit more about the program as we go. So we'll take a look at NextRad. So you can search the data sets by the name. You can also search by tag, environmental, which you'll get back a lot because these are NOAA data sets. But we'll go back to searching by name. And this is really just a way to sort of browse through the catalog and find the data set that you're looking for. But we're going to, of course, bounce into NextRad. And if you're not familiar with NextRad, though I'm sure everyone is, NextRad is over 160 ground radar stations across the continental United States. I think also there's a couple up near me in Alaska. These radar stations, of course, provide the evening weather forecasts amongst a bunch of other things. So there's a lot of really great data. It's near real-time data. It's updated roughly every 7 minutes in the Open Data program. And you'll see as you browse through, there's quite a bit of data on this page, how to cite the data, who to contact if you have a problem. There's also some usage examples. We'll actually look at this Studio Lab example in a moment. Tools and applications. If you cite the data and do a publication, eventually, we're a small team, we'll get to it eventually, we will add your publication to this page. And I can even show you this page. It's in an open GitHub repository. So if I forget to add your publication, if you use this data set from within the Open Data program, just open up a pull request to the GitHub repo and I will add it. But there's a couple things that you can do while you're here. You can look at the type of data that's available, but you can also actually, for most data sets, and I think almost all of the NOAA data sets, you can actually look and see what's in the bucket right from within your browser. So simply click on this Browse Bucket link, and it will show you what's within the NOAA NextRad Level 2 bucket. And you can see that we are sorted by year, month, day, and then a ground station key. Keep in mind, this is the ground radar stations. KBOX, I believe, is the Boston ground radar station. And of course, they're time bound, so we'll go to the end. I'm kind of surprised it says 5 hours ago. So if you want to, you can actually download an item right here within your browser. Simply click on it. It takes, I'm on hotel Wi-Fi, so it's a little slow, but I just downloaded this file. And notice I did not provide any credentials. So this was completely anonymous access. I was able to browse the bucket and look at everything that's in the bucket without providing any credentials. You can do the same thing from the command line interface. Even if you have provided credentials and configured your AWS CLI to have your AWS credentials, by sending this no sign request during when you send the command, your credentials will not be sent over the wire to AWS. So we're simply going to copy this command and open up a terminal window. And this should look really similar to what I just did, just in a terminal window. So you'll see that we are sorted by year. This pre just means prefix. It's another name for folder. So we're sorted by year, month, day, and it's obviously the 19th of July. And then I've got my ground station key, and last time I did KBox. And so I believe I downloaded this one, and I'm going to do the same thing. So I'm just going to paste that and say, go ahead and put that file right in this folder, and the folder that I'm in is called demo. And I'll change the list command to a copy command. And that will very slowly over hotel Wi-Fi download that file. So again, I downloaded a file completely anonymously. I can, run my processing on-prem if I really want to, if I'm willing to wait for all this data to come down. Or I can go ahead and use it right in the cloud. So now I know where the data is in the open data, in the registry of open data. I know how to access it, both from a browser and pull individual files from the command line. But what if I want to do some real analysis now? And maybe I want to use it in the cloud where it will be faster. I don't have to sit and wait for everything to download. So I want to show you SageMaker Studio Lab. But before I click this button, I'm going to go ahead over to another tab where I've actually logged into an account that I created on Studio Lab. I should have created a QR link for you, but it's studiolab.sagemaker.aws. And if you go to that link and click register, you can create a free account. It's an account that you can have for free. You don't need an AWS account. It's actually not linked to your AWS account if you have one. And you will get 8 hours of CPU, 4 hours of GPU. Actually, some of the times have changed. So it's up to 4 hours of CPU at a time with a limit of 8 hours in a 24-hour period, which is roughly 8 hours. And you can see that I've actually started this machine already, and I started a CPU, so my machine is running. So this is a completely free, basically a managed Jupyter notebook server. So you don't have to worry about patching or maintaining this machine. You simply say, I want to run a Jupyter notebook, and you just launch this instance, and I'll show you what that looks like. So let's say I've never really used Studio Lab before, but I want to run this Studio Lab example for Nextrad, which you can get to with this handy QR code. So I'm just going to launch this in a new tab. And you'll see it goes straight to Studio Lab, and it's going to show me the notebook that I'm going to copy into this account. And what we'll say, we'll click on the Copy to Project button, and this will launch just a Jupyter Notebook server, which, there's nothing, super new and interesting about that. But what it does as soon as you launch the notebook, or as soon as you launch the instance, it will ask you if you want to clone this entire repo, which is all the files from the GitHub repo where that notebook is stored. And you want to do that. You want to clone the entire repo. Make sure you do it at the root. And I already have it canned in here for this demo, but it would take some time. It will pull those files over, and then you'll want to build the Conda environment. So again, the Conda environment's already here, but you can see what it was trying to do. It wants to create the Conda environment based on this environment YAML. And this file just says, from these channels, Conda Forge and defaults, go ahead and pull in all of these different libraries and build an environment for me. So since the environment's already there, let's just go ahead and run this notebook. So I'm going to double click on the notebook to launch it. And I have to go down and make sure that my kernel, which is the NOAA or the AWS Nextred SMESL, which is a shorthand for SageMaker Studio Lab, I want to make sure that my SMESL kernel is actually running. So you can see that the numbers, there are numbers here already. That's because I went ahead and ran a couple of lines to make this demo a little bit quicker, and commented out some lines. If you download this SageMaker Studio Lab notebook, you'll see that you actually have to go through these steps. It takes just a few minutes to install, and it's a workaround for a problem with the Botto3 and Cartopy and ARM PyArt libraries with Conda. The interesting part about this notebook is that we're using the Botto3 Python library. And Botto3 is really interesting because it allows you to talk to AWS services. And in this case, we're going to create an S3 connection and start looking at that bucket the same way we looked at it in our browser and from the command line interface. So like I said, we're going to get an S3 connection and we're going to go grab that same bucket, NOAA Nextred level 2, and get a handle to that bucket. So there's just some comments here to explain sort of the formatting. This is a really great notebook. I hope you take your time and read through it. It was actually created by a customer a few years ago. And it's just a really great notebook. We just made it work on SageMaker Studio Lab. So in this case, I'm going to go back to 2011 and grab some data from the KVNX ground station. And then I'm just going to plot some precipitation. And you'll see it changes to an asterisk as it's working. And then once it's done, it changes to a number for that line. And now you can see that we have plotted some nice reflectivity, some precipitation. Now the next one's a little bit heavier duty. This one is actually going to pull quite a bit of data from October 6, 2016. This is a Hurricane Matthew storm that really devastated the southeast United States amongst a couple of other areas that it really kind of hammered. What's nice about this one is that it's pulling in a lot more data, and it creates a really nice visual once it's done. And here it is. Here's the eye of the hurricane. So KAMX ground station, you can see the eye of the hurricane as it is about to make landfall again. And really nice bands. It's just a really great example. So what I would suggest is that if you are not familiar with SageMaker Studio Lab, but you're kind of familiar with Jupyter, just try one of these and see sort of how you can use this to do your own analysis. Again, it's a free notebook server, so certainly take advantage of it. And some folks say to me, I already have an AWS account. Why would I want SageMaker Studio Lab? Well, there's still some use cases. If you're a researcher, for example, and you have, let's say, a really good contract award, and someone shares a notebook with you and says, hey, go try this notebook and see all the cool stuff I'm doing. You may not want to use your contract award dollars to look at that notebook. I would pull it into Studio Lab just to kick the tires and tinker. That's really what Studio Lab is for. When you're ready to do, full-scale analysis, you want to, launch a DAS cluster and troll through a bunch of ZAR files. Then I would go to SageMaker, the For Reals product, or maybe you want to use a feature like SageMaker Geospatial, which is only available in the full product. So that's my demo today, and I hope you enjoyed it.
All right, thank you. Our presentations have been exciting and the video recordings are available. We have a few remaining minutes to take some questions. There are a couple coming in through the chat. I wanted to offer the opportunity for those in the room. We'll take a question from here and take one question from the chat. The questions that are highlighted in the document, we will follow up separately. Some of them are technical in nature and may need input from our cloud partners who are not here. So with that, are there any questions from anyone in the room? It's got to be one. Yes, I see one. All right, there's a mic coming your way.
Hi, Dave Jones with Storm Center Communications. I was just wondering if the GIS web services that are being offered in the cloud, is that associated with NOD? is the Weather Service efforts to get those services in the cloud the same effort, or is it different?
So Dave, thank you for the question. Those are different efforts. My understanding of most of the GIS type of data, right? They have viewers and that sort of thing for you to use the data. The data on NOD is often either the raw data or products, not those kinds of services. Did I make that clear, Jenny? I'm not sure. Feel free to jump in if you have a better response.
I think that did it. Thank you, Adrian. We'll take one more from the room, and then I want to go to the one in the chat quickly. Yes.
Hi, Adrian. Just wondering if there's any.
Sorry, can you please introduce yourself so
sorry,
she knows who you are?
I'm
Yeah.
Carmen Jenkins with Palantir. I'm wondering if there's any thought, you kind of have to know what observing system data or model the data you want is coming from in order to really get to it, I think, on the way the data is organized. I'm wondering if you guys have thought, or if there's any interest from the NOD partners to, leverage like LLM technology to help guide people to the appropriate data or files based on the need they have if they're not knowledgeable on how that data is organized.
That's a great question as well. And right now we are doing that ourselves. Folks write in and ask questions and we respond to them. And so if they have scientific questions, if we don't know the answer, we bring in the scientist. If they have technical questions of the cloud service provider, we bring them in. Often our NOD team can answer the questions because they have a lot of background. We have not talked about any kind of software to date or any other sort of thing. And I do want to, well, anyway, I'll leave it at that.
Yep. Yes, and please use the feedback form to offer comments, reactions, responses. It's a great way for us to understand what you want NOD to discuss and talk about in the future, and also how we can work with ASIP. Okay, a couple of questions coming into the chat. For those of you in the room, we have 1 minute till our session ends. However, I see everyone still sitting in the room, which is super. It's a good thing there's a break right after this. So by all means, unless ASIP folks kick me out, we will continue the discussion for a couple more minutes. Okay, first question coming in through the chat. How do users know where to go for which NOAA data sets, given there are multiple cloud providers? Great question. You had a video demonstration of how to find information on AWS. We really invite you to go see the NOAA NOD website, noaa.gov/NOD. It's as simple as that. But I've also put the link here and will be in the document. Okay, one more from the chat, and then I will go to the document. Is NOAA using the cloud provider storage to meet stewardship requirements as well as access requirements?
NOD is all about access to the open data. That is what NOD is in response to. NOD serves the LO's data, meaning the line offices within NOAA. So the National Weather Service, the National Marine Fisheries Service, right, et cetera. So it's their data that NOD is serving, and we serve it the way the LO wants us to serve it. So stewardship requirements are typically taken care of with the data by the LO. There are some stewardship activities we do, which is essentially make sure that we may go back and rectify to make sure all the data is there, that kind of thing. But with respect to data stewardship, that is done by the LOs.
Thank you, Adrian. With everyone still sitting in the room, I kind of feel pretty
I want to answer Anne's question.
Oh, yes, please.
Okay, so Anne, I appreciate you asked if I could estimate the annual cost of NOD, and that's a really very interesting question. I really appreciate it. And I'll say this, roughly, it is less than 2 million a year. There are two parts to this. One is our relationship with the cloud service providers. These are through contracts. They're very, very low cost contracts, and they are essentially public-private partnerships to deliver this data. There's value on both sides, and that's what the contracts represent. For the users, what they do is provide certainty and confidence that the data will be there and you can build your processes on it, much like Kate Duffy showed her processes today. And then I'll just say the cost is really the small team. You're looking at a couple of us right now. We are a very small, very agile team. We're running on a shoestring, and that's what costs $2 million or less a year. Next question.
Okay. There are a couple of technical questions related to, our existing NOAA metadata and its transformation into the format for STAC. That is something that I think we would like our technical team to weigh in on to respond. Does that seem fair, Adrian? We can follow up with.
We can. Yes. We will follow up, but I will say for now that really that is really a CSP decision at this point. Again, NOD serves the data that the LOs want served out, and the cloud service providers are the ones making your providing you with tools and that kind of thing on their platforms to make it easy. So we've heard, so it's up to the cloud service provider. We will get some responses, though, more specific responses for you. Thank you for the questions.
Yep, and similarly, the follow-up question is, will NOD data be cataloged in STAC where the STAC catalog's located? So deferring to Adrian's previous comment on that too. So it's, but understanding this question is really key. For those that raised it, both virtually and in person, please let us know from a different point of view what you would like to see. So we're capturing that feedback, and that will help us drive conversations in terms of what the demand is. Another question, what is the difference between NWS GIS services in the cloud and NOD?
I think we essentially got that with Dave's question right off the bat.
That's thank you. Okay, one last one, which I think is a good one. How does the future of NOD align with the overall push to push NOAA data in the cloud?
Thank you so much. You all have great questions. So it aligns beautifully. NOD was approved by Congress to support the LOs as they move to the cloud. So there's a lot of effort and work for the individual LOs to move their workload into the cloud. In the meantime, NOD can provide users with access to their data. NOD also provides a centralized coordinated team that works with the cloud service provider. So they go through us, so that it makes it easier for the entire all the organizations to work together.
That covers, oh, go ahead.
I'm sorry, I was just going to say, we love your questions. We'd be happy to answer them. You can always reach us at nod@noaa.gov. Literally, the email is nodd@noaa.gov.
Okay, we still have about 20 plus people in the room. I think they're interested in the conversation. It's 5 past. I invite you to please come talk to me and my colleague Kate. Adrian will be in line for a few more minutes. Thank you again for your interest. And if you have use case, feedback, perspective, experience, or a list of data sets you want to see in the cloud, please, please, please email us and let us know.
Absolutely. Thank you, Jenny. That's
great. All right. Thank you, Adrian. If you can stay on for a minute. Virtual participants, I apologize. I wanted to say thank you for your participation and involvement, and please be in touch if there's anything we can answer for you.
Thank you, everybody. It was really lovely to be here today.
Yeah, good discussion. I'm going to hang around here at the podium for a minute. Virtual listeners, by all means, if there's a question, we will communicate at the mic so you can also hear. But at the moment, there's no one approaching me, which is great. We can go to break. Yes. Okay. All right, thank you, everyone. We will end the session at this point. There is another session coming up, so I've gotten my hands up remark. It's been great. Adrian, virtual participants, and Kate Zura, who's our virtual speaker. Thank you so, so much.
Thank you. Thanks to all our speakers.